called Radial Basis Function Network, RBF network. Okay, so Radial Basis Function RBF. Okay, this is another one interesting network which is used mainly meant for classification, categorization, interpolation, approximation. So for these varieties of problems, the RBF network is used. Generally, it is used. Okay. So far, whatever the networks that we have seen are typically, if you notice, the activation is propagating in the forward direction. And we have seen that from the layer to the layer, so from one layer to the other layer, the activation is getting propagated as the weighted sum of inputs and connection weights. So that is how the activation is getting propagated in the networks that so far what we have learned. Okay, but RBF network uses a somewhat different approach. Okay, essentially the network has two layers. Okay, so I will just show the diagram architecture that is available in the book. So if you notice the architecture is a two-layer architecture. Okay, so where okay, so I'll just are you able to see the image that?
Yes.
Yeah, you can notice that network has two layers. When I say two layers, in fact, if you notice there, you are seeing three layers. So I have written two layers still. So if you notice, you have input, you have hidden, and you have output. Okay. Now the point is, if you see the input to hidden, there are no connection weights. Okay, this is one of the interesting dimension of this network. Okay, and then you have hidden to output, you have connection weights. Okay, you have connection weights. So when the network goes for the training, you need not worry about the connections between the input to hidden. Okay, so because there are no connection weights essentially. So the activation propagates, the input activation propagates from input to the hidden. Okay, so it is essentially two-layer network in the sense that you have you have the calculations and computations happening at the hidden nodes and as well as at the output nodes. Okay, so that's the reason why I have written here the network has two layers. So what are those two layers? Hidden layer and output layer. And input to hidden layer, you have just activation moving. Okay, that means whatever the input that you present, say if it is 0, 1, because it is a two inputs feature vector. Okay, so 0, 1, it just gets propagated to the, it just goes to the hidden nodes. Okay, there are no connection weights. And similarly, when there is a learning, again, I repeat that the learning actually happens here. Okay. So when I wrote here the weighted sum of inputs and connection weights, since there are no connection weights between your input nodes to the hidden nodes, your activation is not like, the input multiplied by the connection weight. Okay, so that is not there. But whereas output from the hidden, okay, so since you have the connection weights between hidden to the output nodes, output from hidden would go as input by multiplying with connection weights. Okay, that goes as usual. So output from your hidden nodes W1, W2, W3 and W4, they go as multiplied with the corresponding connection weights here, and that goes as the cumulative input to the output neuron. Is that clear? Is that clear? Yes. So far, whatever we discussed?
Yes, sir. Yes, sir.
Yeah. So this is how the network works. Now let us go further. So we have seen so far that the activation is just propagating, and we have seen that we understood that there is no connection weight between hidden to input to hidden, and you have only the connection weights from hidden to output. Okay, so these are the this is how the network actually propagates, and this particular network, in fact, works faster because you have only two layers, so it actually goes faster than typical MLP models. Okay, our multi-layer perceptron models, right? So it goes in a very faster manner. And actually, the network, the RBF network, has its biological connections, or the biological inspiration coming from locally tuned overlapping receptive fields. Okay, when I say locally tuned overlapping receptive fields, and this is the biological inspiration coming from the human brain, especially that is there in the cerebral cortex. These type of fields are there in the cerebral cortex, visual cortex of the human brain. Okay, what do you mean by this locally tuned overlapping receptive fields? Okay, so take an example. It is like this. We all know that recently there was a video that got circulated in the news about the volcano getting eruption in the in one of the region at Pacific Ocean, especially in the country called Tonga. Have you heard that, and have you seen that video in the news? Yes, so if you have noticed that particular video, what happened, that's a beautiful video showing the satellite video capturing of the volcano eruption and subsequent propagation of the tremors. Okay, so means at a point where the volcano has erupted, you can notice there is a big bubble, and slowly that particular waves getting propagated in the 360 degrees in the in the video. Have you noticed that? So if you notice there, this is the center of the that particular volcano eruption. In the 360 degrees, you would have noticed that the that particular waves, the tremors or waves have got propagated. Have you seen that video? If not, you can just Google it and then see it. But the point what we want to understand there is that the exact center where that particular eruption has taken place, you would have seen the magnitude of that particular effect at a more. And slowly when the waves gets propagated in the 360 degrees, that means that when they move away from the center of that particular region, slowly they get decay, right? The decay happens. So now this is one typical example. Now similarly, when you look at the human brain, what happens is there are certain, whenever you look at certain activity, the human brain, you will notice that parts of the human brain gets activated. Okay, and not only that particular part, but also the surrounding parts. Okay, so when there is an activation at a particular region, not only that particular region, but also in a specific boundary, in that particular boundary, there would be a region that's get activated. Okay, so this is what is actually is there in the human brain, which is called locally tuned overlapping receptive fields. Okay, and it is nothing new in our this thing. So take an example, whenever you are reading operating system, generally when we talk about memory management and memory optimization and all that, we see that if there is a concept called when you access a particular memory page or a segment, it is more likely that the process that is accessing a particular page also try to refer to the nearby pages. Okay, so that's the reason why when the particular page is getting pulled from the disk to the memory, it is likely that the nearby regions also gets copied. So it's a kind of memory optimization. So these things are already there. So the RBF network, what it is doing is it follows the similar kind of analogy here, and the network is designed in the sense that the network goes like this. The entire working of the network goes like this. Okay, so the entire network goes like this. What we do is typically you notice on the hidden nodes. Okay, what we are doing is at the hidden nodes we take prototypes of the training data. Okay, what do you mean by prototype? So it is like a the representation of the training data. So in this particular network, you can notice that you have totally 1, 2, 3, and 4. That means the overall data is having 4 prototypes. Okay, so imagine I have about 1,000 samples. From that, I am creating 4 prototypes, or I can call it as 4 clusters or prototypes. Okay, so these 4 clusters or 4 prototypes form my hidden node. Okay, so each hidden node is a prototype or a cluster having cluster center. Okay, so when there is a cluster, obviously there is a cluster center. Now you notice here that particular cluster is represented in the form of a hidden node called R1, R2, R3, R4. So each cluster is there are about totally 4 clusters, and there are 4 prototypes. Are you able to follow what we are discussing here?
Yes, sir.
So we are taking the okay, let me go to the next slide and try to explain. So how you are going to handle the RBF network? So essentially the RBF network, you are going to take your total input and divide the input into training and testing. Okay. So anyway, we are not going to touch the testing. So the testing comes only after training. So what happens with the training? Now take the training data. Okay. Then identify how many number of prototypes you want to create. Okay. This is one of the heuristic. When I say number of prototypes or clusters you want to create. Imagine you wanted to make it about K clusters or K prototypes. Use an algorithm such as K-means clustering that allows you to form K clusters. Okay. And when you form the K clusters, what happened? You are going to have, of course, we are not going to discuss here K-means clustering. So essentially K-means clustering goes like this. So once you identify the number of clusters from the given input data, it is an iterative procedure. Okay, remember K-means clustering is an iterative procedure where for every cluster you choose one random centroid. Then over the iterations, you allow that centroid to settle down exactly at the center point. Okay. So that is how the K-means clustering procedure works. And for that settling down the center, it uses a distance measurement metric called Euclidean distance or some kind of a distance measurement metric. So, and that is how your K-means clustering is going to form K clusters, and where each cluster is also going to have the centroid or the center point of that particular cluster. Okay. So once that is done, what we are going to do is we have now these cluster centers and clusters. Clusters are going to serve as your RBF radial basis function nodes at hidden layer. Okay. So your hidden layer nodes are nothing but your cluster centers and the clusters and cluster centers serving as your hidden layer nodes, or you can think even them as the prototypes. Up to here, whatever we discussed, is it clear? Is that clear what we have discussed so far?
Can you explain the K-means cluster?
Sorry, can you please?
The K-means clustering algo.
Okay, so K-means clustering is another algorithm, which is an iterative algorithm. So what happened is the K-means clustering, when you give the samples, okay, it tries to identify the clusters and form the clusters. How it forms the clusters? Okay, say take an example, you wanted to form say 3 clusters. Okay, so take an example 1 and say take an example, okay, something like this. Okay, and something like this. You wanted to form 3 clusters. Okay, you think like this. Okay, so there are about 3 clusters you wanted to form. So for that purpose, what actually it will do is it will try to identify initially initially with a random cluster center. Of course, if you notice for these 3 clusters, you may be having the cluster center somewhere here. Okay, but initially it chooses randomly a cluster center, and through an iterative procedure, it identifies finally what is the exact cluster center. Okay, so that is a k-means clustering algorithm. Okay, so for that purpose, it uses a distance measurement metric wherein which you are going to identify what is the distance between every sample in the cluster to the cluster center. And center is supposed to be at the center point. So using that distance between the cluster, the points in the cluster and the cluster center, it will identify the cluster center and forms the three clusters. Now these three clusters are the prototypes, form three RBF nodes. In this particular example, what I have narrated here, you have three nodes. Imagine in the previous slide, you have seen four clusters or four prototypes. Okay. Okay. Is that clear?
Yes, sir.
Yes, sir.
So now your hidden nodes are your prototypes. Prototypes of what? Of your training data. And these particular the centers are the centers of your cluster centers. Okay, the nodes, the centroids of the clusters are nothing but the centers of the clusters. Now what we do for each input vector in the training data, what we do, we calculate activation. Okay, so we calculate activation. When I say activation, what is that activation you are calculating? If you see in the previous this thing, you are just submitting the input. Okay, so you take the input vector and submit it. Now we calculate the activation at hidden. Okay, so we calculate activation at hidden layer. So for every hidden nodes, that means every prototype node, we are going to calculate the activation. How we are going to calculate it? It is through the Gaussian function defined as psi of x. Okay, psi of x, where psi of x is equal to e power minus x minus your cluster center x cap, or else some of the literature they write it as mu, x minus mu square by 2 into sigma I square. Okay, I write it here again, e power minus x minus mu square by 2 into sigma I square, where this x is the input vector, whatever that we have given, the input that we have submitted at the input layer. The mu is your cluster center, that means the prototype center. Okay, that is the cluster center vector. And now there is another parameter here, x minus mu square. The other one is sigma I square. Okay, now generally while calculating, we take this entire term 1 by 2 sigma I square as beta. When you write it, what happens? Your psi of x is equal to e power minus beta into x minus mu square. Now, what is this particular beta term? Okay. So this particular beta term, or 1 by 2 into sigma I square, is the one. The beta is the term that is going to define the height of your Gaussian function. Okay, we will see what is this height of Gaussian function. Okay, we will see in the next this thing. So we'll see in the next slide. So the point is, so far what we discussed, we said you take the training data, form some number of clusters. Even you can define the number of clusters heuristically, whether k number of clusters or k plus 1, k minus 1, whatever it is heuristically has to be decided. And then Once that is done, you are going to form the clusters at the hidden nodes. In fact, hidden nodes are nothing but the clusters, and you submit each input vector of the training data. For that, we are going to calculate the activation, wherein which the activation function is psi of x is defined as e power minus x minus mu square by 2 into sigma I square, where x is the input vector that what we have given, mu is the vector representing the cluster center. When I say this particular node, this particular cluster center, excuse me, that is represented as the mu, and 2 into sigma I square, which is going to represent the height of the Gaussian. So how do you calculate that height of the Gaussian? Generally it is calculated the height of the Gaussian as so height of Gaussian is equal to the average distance between all points in the cluster and cluster center. So that is 1 by m into sigma I is equal to 1 to m xi minus mu. So that means, imagine you are at a particular cluster. What you are going to do is, for every point in that cluster, the distance between that particular point and the cluster center. So that is the average you are going to verify, and that is going to define your beta. Okay. So when you do that, what is this m? Total number of samples in the cluster, number of data points in the cluster, and xi is the ith sample, and your mu is the cluster center. So what you are going to do is you are going to calculate the average distance between all points in the cluster with the cluster center. That is going to define your height of the Gaussian. Now, once that is done, this is the activation from one particular node in the hidden layer. So like this, you are going to calculate the activations from every node in the hidden layer. Once that is done, the output from hidden nodes is served as input to the output layer, and that is gets multiplied by connection weights. Remember, we have connection weights between hidden nodes to the output nodes that we have mentioned. So output from this hidden nodes is going to be multiplied with the connection weights between your hidden nodes and the output nodes, and that would be served as the input to the output layer. Once that is done, what we are going to see is that we have to train so training happens is through adjusting connection weights of hidden to output. So what do? I take output layer nodes. I see what is the target. So when I submit an input, what is the corresponding target at the output layer? I verify by calculating the error function. Okay, I check through error function, and typically the learning happens, the calculation of the error, adjusting the learning, adjusting the connection weights happening happens, the learning happens via your delta learning rule. All of you remember the delta learning rule that we discussed when we talked about the ADA line. Okay, so the typical ADA line, okay, the way the activation propagates from your hidden to output, and output you are going to verify the targets and adjusting the connection weights between hidden to output happens via delta learning rule. Okay, this is how a typical RBF network works. So again, I repeat, what we have done, you have taken the data, overall data. From that, you are going to divide it into training and testing. For the training data, you are going to identify on a heuristic basis how many clusters you wanted to create. And the clusters would serve as the hidden nodes in the RBF network. Okay, imagine I am creating K clusters and you are going to have K number of nodes in the hidden layer. And cluster centers would also serve as the prototypes. Now what we do, you take each input vector and pass that input vector to the cluster nodes. That means the RBF nodes. Every node would calculate the activation through the Gaussian function, which is defined as like this: e power minus x minus mu square by 2 into sigma I square. Once the activation is calculated, the activation goes to the output layer. When it is going to the output layer, it is a typical weighted sums. That means output from the hidden multiplied with the connection weight at the hidden layer to output layer. When you multiply it, you get the input to the output layer nodes. And remember, output layer nodes have the targets. And adjustment of the weights happen through the delta learning rule. And once the weights are adjusted, now you take the second input vector, third input vector, the fourth input vector, fifth input vector. So once the entire training vectors are completed, your training is done. And once the delta learning rule settles down, your training is completed. Then you take the testing samples and test the network. That's how your network RBF network works. Is that clear? Okay. Now let us take a little more illustration to understand this particular network. So you can see a better picture of RBF neurons. Now you are taking the input vector. Now remember, the RBF neurons that are there in the hidden are the prototypes or the clusters. Now you notice this is your Gaussian function, which is in the form of a bell shape. Okay, remember when you have seen the Gaussian function, okay, psi of x is equal to e power minus x minus mu square by 2 into sigma I square. This is the formula. Now imagine if my input vector that is given is the exact cluster center. That means, you know, this becomes 1. You are at here. Okay. Imagine this. If the input vector is belonging to this, say, take an example close to this particular cluster. So you are at here. Okay. If it is at exactly at the center, if it is exactly the center of the cluster, then imagine this is the cluster it belongs to. Then you are at here. Imagine if it is little far away from the cluster, okay, maybe it is at here, it is at here, it is at here, kind of a thing. The more it goes off, obviously it goes 0. Slowly it goes 0. And when it is going to 0 to this particular cluster, means probably it may be close to this cluster. Okay. So when it is at this particular cluster center, that means it is 0 here for the other centers, other clusters. Okay. And what is this 1 by 2 into sigma I square? The beta parameter is, this is the height or the distance of this, or the size of your Gaussian function. That is what is your sigma defines, size of the Gaussian function. Now, if you notice this particular diagram, input to hidden, there are no connection weights. Okay. Now, output to hidden, you have connection weights. Okay, you can notice that. Now, when I submit a input vector which is belonging to this particular cluster, imagine if it is close to this particular cluster, obviously this neuron will fire and rest would fire 0. Okay. And similarly, when the training happens, you are adjusting weights, weight adjustment through delta learning rule. Okay. And remember, you have, in this particular case, you have C category, C number of nodes in the output layer. So corresponding targets would be fixed for the input. And accordingly, the delta rule will adjust the connection weights. Okay. Now we will try to understand little bit the cluster centers also for our better understanding purpose. I'm just trying to, in fact, I was last few days, I was trying to get some better illustration for the RBF. So fortunately, I have got it in one of the blog. I'm just trying to get that images and then show it to for your better understanding purpose. So 6th. Okay. I hope all of you are able to see the screen, right? So now you can notice you imagine you have a data. Okay. The data has two categories. That is the blue samples and the red samples. What the designer has done for the blue samples, he selected 10 clusters, and for red also he has chosen 10 clusters. Okay. Now you can notice this is one particular cluster at the. Are you able to see? That is shown with an asterisk. Are you able to see that?
Yes, sir.
So this is one particular cluster center. This is one particular cluster center. So it's 1, this is 2, say this is 3, this is 4, this is 5, this is 6, and this is 7, and this is 8, this is 9, and this is 10. Okay, so totally 10 clusters for blue, and similarly 10 clusters for red. So there are two categories, and there are n number of samples of training data. So what he did was he has chosen these 10 prototypes for blue samples, these 10 prototypes for the red samples. Okay, and he has used, in order to do this particular exercise, the k-means clustering algorithm. Okay, so which is trying to identify the cluster centers. Now this is the cluster, and for that this is the center, and this is the cluster. Okay, for that this is the center, And now this is another center, this is another center, this is another center. So cluster centers are identified. Now what happened is the network, once the cluster centers are identified, you present the sample inputs. Okay, so for every sample input, okay, you can see another diagram which is a a 3D mesh which is trying to show these cluster centers in a better manner. So you can see that also. I'm just putting it. Yeah. So now you can notice that. Okay. So look at this. Look at this particular. Say, take an example. This particular cluster. Okay. So you have a cluster center here. And similarly, look at this particular cluster center here. Now the point is, imagine you have a data sample. Once these cluster centers are formed through k-means clustering algorithm, imagine if you take a sample and present it as an input. What is that Gaussian function it is doing? It is trying to identify the distance between that particular input what you are giving, and for every cluster, what is the distance? Now imagine if that sample is in this particular center. Okay, imagine that it is in this particular cluster. Obviously, it is close to this particular cluster center. Now for the rest, it is 0. Okay. So then what happens? You will have activation coming from this particular cluster center, and from the rest of the other clusters, the activation would be 0. And that activation propagates to the output layer. Okay. I hope now you got a better clarity. Hello?
Yes, sir.
So you can take the the diagram. So now if you notice, when you proceed further, what happens is when actually the learning completes, you can notice that, okay, this is a kind of a the line that is drawn here is a kind of a decision boundary. Okay, kind of a decision boundary that is categorizing blue and your red points. Okay, now imagine I am submitting a red sample. Now what happened? We check to which cluster center it is close, and that particular category output you will be getting. Imagine I am taking a testing data, and which category it is false. Obviously the network would be able to identify it if the training is complete through the delta learning rule. Okay, so the RBF network, as I've already said, it is faster than the your MLP and other models. And but only thing is that it requires the more number of the more number of your hidden nodes. If the more number of hidden nodes, that means more prototypes, better would be the accuracy. More the number of prototypes, better is accuracy. Okay. So this is the illustration of RBF network. Now your textbook contains the algorithm. Let us have a look at that algorithm, what is given in the book, so that you can just give me a moment. I'll just just trying to get this one. Hope you are able to see the algorithm. So when we say set the weights to small random values, these are nothing but your hidden to output nodes. Okay, so perform steps till condition is false. What is the condition? Your delta learning rule till it goes. Okay, remember these things are not explicitly given in the book. Now what you do for each input units, what we are going to do is we are going to calculate the radial basis function. When we say step 4, in fact, you are going to do the step 5, where we are going to select the cluster centers, and that would be forming your basis, or that would be forming the prototypes. Once that is done, you are going to submit each input, and for that you are going to calculate the output from the hidden nodes. So the formula is given there. Okay. Just give me a moment. Excuse me. So once the activation is calculated, finally we are going to verify the output of the neural network by adjusting the connection weights. Now if you look at the input to the output nodes, it is the output from the hidden nodes multiplied by the connection weights, and remember that W naught is the bias term. Okay, so this is the bias term at output nodes. Okay. So you verify the error and test the stopping condition, and of course the learning happens via your delta rule. Okay. So this is how the radial basis function networks works, and we have seen the applications of the network in the beginning, for what purpose it is used. Okay. That's all. So we will be discussing the